Hello and welcome to the Open Security Training Architecture 1005 RISC-V Assembly. I'm Zeno Kova and I'll be your instructor for this class. So about this class, we are going to be doing a top-down class in which I assume that you know a high-level language like C, which is one of the lowest level high-level languages you can use, and we're going to use C source code, compile it, generate RISC-V assembly, and learn about the new assembly instructions as we see new elements of C code introduced in our new examples. This top-down approach is contrasted with a bottom-up approach where I would just teach you individual assembly instructions like this is an add, this is a subtract, and build up small programs from that. I feel it's better to teach based on something you already know, like the C programming language, so that fundamentally your brain has something to hang this new knowledge off of. You can say, oh, I know that calls in C programming correspond to JAWs in assembly language for RISC-V. The other point is that this class is intended to expose you to the most common assembly instructions in both 32-bit and 64-bit RISC-V. So it is intentionally not going to cover some of the other aspects such as floating points, vector extensions, privileged assembly instructions, transitions from user space to kernel space, and so forth. Those are topics that would be reserved for future classes, such as a future Architecture 2005 for OS internals on RISC-V systems. Now, the miscellaneous that I'm obliged to tell you up front is that this RISC-V is not pronounced RISC-V, it's pronounced RISC-V. And that's because this is the fifth iteration of the Berkeley Reduced Instruction Set Computer, or RISC architecture. And I think we all remember in Hackers where Kate Libby told us that RISC architecture is going to change everything. And Dade said, yeah, RISC is good. So if you're curious about the genealogy of RISC-V and what RISC 1 through 4 are, you can go ahead and check that link at the bottom of the screen, which will be posted after the video. You'll see that by 1990, they were already on RISC-IV because they had started the RISC architecture back in the 80s. Now, perhaps you've heard of RISC-V, but you don't know where exactly it's used these days, but you're curious enough to take this class, and so let me give you a couple of anecdotes about different places it's used and some of the players using it right now. The first and most important one would be Sci-5. This is a company that is founded by some of the core RISC-V architects, and consequently its whole goal is to push RISC-V forward as a useful industry-usable technology. To that end, they focus on an important element of silicon ecosystems, which is developing intellectual property, or IPs. So you create an IP and then you sell it to another company, and then they can sort of just plug and play and put that thing into their existing silicon manufacturing. So some particular subcore of a system on a chip could be a RISC-V core, while other cores could use other technologies. And so Sci-5 is focused on spreading RISC-V technology through intellectual property development, licensing, selling, and so forth. Although I should also say that they are one of the primary companies that's focusing on trying to show that RISC-V can work as a more high-performance computing platform as well, not just embedded systems, but all the way up through mobile phones or small computers. But today, as I write this class in 2024, the place where RISC-V is most prevalent is at the embedded system, at the lower end of the architecture. And so we can see embedded system makers like Western Digital, who are makers of hard drives and solid-state drives. They use RISC-V for their hard drive controllers, the little chip that's on the hard drive that tells it what to do. And this is relevant to firmware security people like myself, because I remember back in 2013 when there started to be security researchers who were finding vulnerabilities by which they could have arbitrary code execution on Western Digital drives firmware. And indeed, later on, based on the leaks by Edward Snowden in 2013, it was recognized that places like the NSA may already have hard drive firmware infection capability. And also later on in 2015, Kaspersky showed documentation of actual in-the-wild hard drive firmware infection capabilities that of course were heavily implied to be NSAs. So in 2013, the researchers would have been looking at hard drive controllers from Western Digital that were using ARM-based systems, but today, if they wanted to do the same sort of research, they would need to learn something about RISC-V. Similarly, competitors like Seagate are also invested in the RISC-V ecosystem and are using that for their controllers on their hard drives and solid-state drives as well. There's this awesome link here when I was just searching around for RISC-V things, talking about the new HAMR technology, heat-assisted magnetic recording that's increasing the densities on hard drives, and it's got a whole bunch of awesome words in the article like plasmonic writer, nanophotonic laser, photonic funnel, and quantum antenna technologies. So perhaps RISC-V is the least exciting of those keywords, but RISC-V is definitely there. Now, apropos to my current firmware security interests, we have Expressif, which is a maker of Wi-Fi and Bluetooth chips, Bluetooth being my current research focus, and they decided in 2022 that they were only going to be using RISC-V for all their new chips. And so they already have chips that are out, and they said, we like it well enough that we're just going to keep going with all RISC-V from now on. In the automotive sector, there's Renesas as a maker of microcontrollers used by vehicles, and in 2021 they announced a partnership with Sci5, and they said they were going to work on automotive systems that were RISC-V based, and in 2023 they did release their first RISC-V based platform. Although when we look at their page for the current chips that are out, they say that they are focused on targeting motor control applications, and it's for efficient handling of brushless DC motors. So that's an interesting use case I wasn't even aware of. And the final anecdote is that Bosch, Infineon, Nordic, NXP, and Qualcomm have invested in a joint company in 2023. It went through the regulatory approvals, and in 2024 it was named Quintaris. And so this jointly invested company is for the explicit purpose of furthering their goals of using RISC-V and creating more standardization in the ecosystem so that they can all benefit from the RISC-V technologies without fragmentation that can occur when you have an open source instruction set architecture that people can just customize to their heart's content. So those are some places that RISC-V is used already today, but why should you learn about RISC-V? Why is it a technology that's going to be worth knowing in the future? Why is it not just going to be relegated to the dustbin of history? Well, in my humble opinion, RISC-V is important to know about because there is a fundamental economic incentive that will lead to more and more silicon makers adopting it. And it will displace more and more alternative RISC architectures. MIPS is a good example because MIPS has been on the downswing for a while, holding on primarily in some networking spaces. But ARM, of course, is the big player in RISC-based architectures and especially embedded systems, and they are definitely feeling the heat from RISC-V. And so the core issue is that ARM is a company that makes its money through licensing. So they don't actually build the silicon, they license out the intellectual property to other companies to build the silicon. Fundamentally, if you want to build a chip that is based on ARM's instruction set architectures, you're going to be paying a licensing fee. So companies necessarily will say, well, if I can use RISC-V and not pay a licensing fee, why should I pay you a licensing fee, ARM? And ARM is quite concerned about this fact. It makes RISC-V a fundamental threat to its core business model. And indeed, when you tell silicon makers, hey, you can still sell chips, but just not pay the ARM licensing fees that you're paying today, well, they say, you had my curiosity, but now you have my attention. Another fundamental reason why RISC-V is worth knowing is because we've actually seen this sort of business dynamic play out before in the context of Linux and other Unix-based operating systems. Previously, there were things like AIX, HPUX, or Solaris, which were fundamentally proprietary Unix derivatives, where you would have to pay some company for the privilege of using that operating system. Linux came in and it fundamentally changed the economic models as companies saw they could do the same thing with Linux, but not have to pay anyone for it. Other than, of course, their system administrators, programmers, but those are the same sort of people that they were paying anyways. So in that sense, RISC-V is the Linux of instruction set architectures. It is an open source instruction set architecture, and consequently it benefits from all of the advantages of open source things. But if RISC-V is the Linux of instruction set architectures, I personally like to think of open security training too as the Linux of training platforms. It's open source, and fundamentally, I think long term, that benefit is going to eat some other platforms. Anyways, Throughout the rest of this class, there is an optional book. There will be only scant references to it, so it is definitely not required reading. But if you'd like to pick up the RISC-V Reader and Open Architecture Atlas by Patterson and Waterman, those are some of those architects of the RISC-V ISA. And there is at least a couple of diagrams in the class that come from that book that are fundamentally more valuable than what you find in the open documentation. But let's finally get into what we're going to learn in this class. In this class, we're going to see high-level source code like this hello OST2, and it could look like this. Here's an example of what that code compiles down to with GCC 7.3 on JS Linux. That is a JavaScript-based Linux that runs entirely in the browser, and it actually does have support for RISC-V. So if you compiled it with that, you'd get this. If you used Compiler Explorer at godbolt.org, then you would see this code instead. But that alternatively could be represented by compilation with Clang in Compiler Explorer. And Compiler Explorer can show us what GCC might compile, what Clang might compile, so all sorts of different options. But fundamentally, it's going to boil down to this. In our class, we're going to be using GCC 1.4.0 inside of QEMU, an emulation environment where it will be supporting RISC-V 64-bit. And so if we compiled our hello OST2 with optimization for size, it would boil down to these assembly instructions. But I want you to take heart. There's actually not that many assembly instructions that you really need to know in order to understand the majority of code that's out there. By one estimation, so I've cited it here at the bottom of the page, just 20 instructions make up 91% of the code for 32-bit RISC-V and 86% of the code for 64-bit. And indeed, because they did this statistical gathering over the Spec 2006 benchmarking programs, this actually is overrepresenting some things like floating point that we don't cover in this class. It's showing up here as one of the most frequent things, but that's just because these are benchmarking tools. So I wanted to see something a little more realistic to what we're going to see in the class, so I went ahead and collected statistics over our final lab in this class, the Carnegie Mellon binary bomb, compiled for RISC-V. And this is what I saw. Total, we have 53 instructions, but you can see that the frequency of a few of these down at the tail end of the graph is extremely small. You may not actually see those. Those may be in there just as extra code that's compiled in as a consequence of using the standard C libraries, for instance. So 53 for total possible understanding, only 25 instructions to get the top 90% of the code, and only 10 instructions to get the top 2/3, 67.5%. So 10 instructions gets you 2/3 of the code, and you've already seen 7 instructions in just the hello world. So we're going to be learning the RISC-V base integer ISA instruction set architecture, RV32I. That has 40 instructions, but it's an easy 40 in that it's mostly variants on the same thing. There's actually, let's say, I want to say 15 of those are just shifts. So then we're also going to learn the base 64-bit ISA, RV64I, and that just adds 15 instructions above and beyond the 32-bit. And those are just variants on the same theme, but they're using 32-bit registers while you're in 64-bit mode. And that's the only real difference. Functionally, they're exactly the same. And like I said, you've already seen 7 instructions just looking at the simplest version of hello OST2. So all in all of these instructions in this class are going to boil down to these 9 themes. Loads and stores, adds and subtracts, Boolean operations with AND, OR, and XOR, shift left, shift right, setting a register 1 if it's less than some other values, branching if equal, not equal, less than, or greater than, so just branch instructions to go somewhere based on some condition, jumping and linking, so that's an important characteristic, the link element of jumping somewhere, linking to a register for how to get back, and then loading 20-bit upper immediates and adding 28-bit upper immediates to the program counter. So not all of that needs to make sense yet. We'll get into all of it, but this is just to say, even if it's 40 instructions or 55 if you count the 64-bit stuff, this is still really just these 9 themes and stuff like add and subtract, load and store. That's going to be simple. So there's not really going to be a lot of complexity here, and that's one of the benefits of RISC architectures. Simpler instructions that don't do a whole lot of things. Sometimes you might need to use more instructions to do something than you would on a complex architecture like Intel, but it's more instructions that are each simpler rather than more instructions that are each more complicated to do more things in one instruction. So the outcome of this class is that by the end of the class, I expect you to be able to know all the RISC-V general purpose registers and their alternative ABI or application binary interface names. Those are the more human-friendly names. Understand how data like local variables, frame pointers, and return addresses are stored on the stack. Understand function calling conventions. So what are the conventions for when we call into and return out of a function? Be comfortable writing some C source code and compiling it down and reading the consequent assembly language that you would see if you looked at it in a debugger. And I, of course, want you to feel comfortable reading the fun manual on your own, because I would be doing you a disservice if I didn't give you the tools to continue to explore on your own without my help after the class. So I really want to teach you to fish in this class and make sure that you can read the fun manual. And finally, you should be able to read assembly well enough to determine the expected inputs and influence the control flow of the opaque binary that we're going to use as our final lab, which is the famous or infamous Carnegie Mellon binary bomb. It's just an opaque binary where it just says, hey, hi, I'm the bomb. You put some input in, and if you don't give the right input, it blows up. You want to avoid the blowing up, so you need to read the code and figure out what it expects out of you to not blow up. So yeah, that's the outcomes of this class. All of that will be yours. So I hope you're excited to learn more about RISC-V assembly. Let's go.